Welcome to our lecture on regression analysis. The purpose of this lecture is going to be to give you kind of a gentle uh, overview and conceptual overview of regression analysis. Regression analysis is a topic that could really be an entire course, much like ANOVA. You could take an entire course studying different types of ANOVAs. The same goes for regression analysis. So we're going to just cover the basics. My goal is that you'll be able to understand how to interpret at least basic output from a regression analysis. I won't really require you to conduct one as part of the final exam, but you should be able to interpret the results of a regression analysis. So basically, a regression analysis looks at the relationship between predictor variables. You could think of these as independent variables or explanatory variables. Predictor variables and a criterion or an outcome variable or a dependent variable. So it's similar, it's very similar to ANOVA where we have an independent variable. Well, here in regression we may have several independent variables and we're trying to see what their relationship is with a dependent variable. So first and foremost, it's important to know the distinction between predictor variables, which are the ones we're trying to explain the criterion or dependent variable with. So the type of regression we're going to just briefly touch upon today is called ordinary least squares regression. So there are many different types of regression, but probably the most common type is an ordinary least squares multiple regression analysis. So we'll be talking a little bit more about what that is in the near future. There are two main reasons why one might conduct a hypothesis test, or rather to conduct a regression analysis, and that is to either conduct a hypothesis test where you're trying to basically address a correlational hypothesis about the relationship between predictor variables and an outcome variable, or alternatively to predict the value of an outcome variable provided the value of a predictor variable with an equation. Now, in order to predict outcome variables with great certainty, you would need really good equations. So there should be relatively low levels of error in order to try to make decisions about an individual case or an individual score based on several predictor scores. In order to test hypotheses, we still need some accuracy. We still need to be able to rule out, let's say, chance as being an explanatory factor in our model, but we don't need necessarily the same degree of extreme precision as would be needed if we were using a regression analysis to make predictions. So there are several assumptions for regression analyses, some of which are that the dependent variable is an interval ratio or continuous variable. So the dependent variable, much like in the case of an ANOVA, cannot be a nominal variable. It probably should not be an ordinal variable unless the ordinal variable has many categories and we can just treat it as a quantitative continuous variable. The predictors in the regression analysis may be continuous interval ratio variables or categorical. If they're categorical, sometimes special procedures are needed to enter them into the equation. Those procedures are often called dummy coding procedures, but we're not going to cover them in this lecture. But do know that predictors in a regression analysis may be either interval ratio or categorical. Basically, what we're doing in the regression analysis is we're seeing, do the predictors, and to what degree, in what direction, do they predict the outcome, the criterion. Now, the first form of regression we're going to talk about briefly is simple regression. A simple regression analysis would just have one predictor. It's very unusual to see a simple regression in the wild, if you will, but it's nice to have that as our point of departure when we move on to multiple regression. A multiple regression analysis is a type of regression analysis that simply has multiple predictors. So instead of having one predictor, as in the case of a simple regression analysis, a multiple regression analysis would have more than one predictor, so 2, 3, 4, 5, what have you. Alright, so looking at here, this is a scatter plot matrix. So we have scatter plots of a bunch of variables contained within this matrix. Let's just pretend we were planning on predicting GPA, so grade point average, with three predictors: hours worked per week, intelligence, and motivation. Right? Now we could look at the correlation of hours worked per week with GPA. We could look at the correlation of intelligence with GPA, and we could look at the correlation of motivation with GPA. And that would tell us the bivariate relationships, but there might be some overlap in their prediction. So let's say if intelligence and motivation are correlated, then just looking at the bivariate correlations themselves may not give us a complete picture. Let's just pretend this is not true, but let's just pretend that hours worked per week predicts 40% of the variance in GPA. Intelligence predicts another 40%, and motivation predicts another 40%. We could not say that we're predicting 120% of the variance in GPA because there is obviously some overlap in the prediction. So really what we're trying to do in a multiple regression analysis is determine the relationship between each predictor and the outcome after statistically controlling for the other predictors. So in a multiple regression analysis, we'd want to see what's the relationship between hours worked per week and GPA after controlling for intelligence and motivation. What's the relationship between intelligence and GPA after statistically controlling for hours worked per week and motivation? What is the relationship between motivation and GPA after statistically controlling for hours worked per week and intelligence? So basically, in a multiple regression analysis, we're attempting to partial out the effect of the other predictors in an attempt to isolate the relationship of our focal predictor and the criterion. So in a simple regression analysis, the equation is fairly straightforward. It is that the predicted value of the outcome of the criterion, here we'll have that as y with an apostrophe next to it. That's the predicted value on the basis of the equation. Y would be the actual value. Y prime would be the predicted value. Equals bx. So b is what's called the regression slope, or more specifically the unstandardized regression slope. It is literally the number of units the criterion, or DV, increases for each 1 unit increase in the predictor, where x is the predictor. A in this equation is the y-intercept, or alternatively, the predicted score for the criterion when x, your predictor value, is set to 0. It's also sometimes called the constant. So taken all together, we have a regression equation that is the score, so the observed score, equals the unstandardized regression slope times the score on the predictor value plus the constant, or y-intercept, and then also plus error. So each individual score is going to likely have some error involved. It would be extraordinarily unusual, maybe even impossible, for the regression equation, with real data anyway, for the regression equation to have no error in prediction of the outcome. That's why we add symbolically, anyway, the error component to the equation. Alright, so just to reiterate a little bit, the regression slope, sometimes called weight or coefficient, it can be standardized or unstandardized, but for now we'll talk about unstandardized. The unstandardized is basically the expected or predicted change in y, the outcome, or the criterion, for a 1 unit change in x. So every time x goes up, how much is y expected to go up or down if it's got a negative sign. So you can interpret these somewhat similarly to a regression coefficient. The sign basically tells you the direction. The quantity of the number tells you the strength, but they are not in standard deviation units, so they're not standardized yet. All right, the y-intercept is basically your predicted value of the outcome when x is set to 0. So whatever 0 means for x, whatever it means, that's the predicted value of the outcome. That's the y-intercept. When x equals 0, what do we expect the outcome to be? Sometimes it can kind of be a nonsensical number, because if our predictor is age, and we enter it in raw scores, and 0 would mean an age of 0, so it would be the predicted value of the outcome when age equals 0. So it's not always a very meaningful component of a regression equation, but it's important nonetheless for it to be a part of the equation. All right. It can also be thought of as the point at which the regression line intersects or crosses the y-axis. So we're not going to really do much of this by hand, because it's very time consuming and prone to errors. But for a simple regression equation, the formula for the unstandardized regression coefficient, actually if you already have the correlation between the x variable and the y variable, the x being predictor, the y being the outcome, if you already have that correlation, it's simply multiplying that correlation by the standard deviation of y over the standard deviation of x. So if you have these components already, it's pretty straightforward to compute. If you don't have the components yet, then you'd want to use a somewhat more cumbersome formula, but one that we could work through. Another way to define the unstandardized regression coefficient would be the covariance, which we covered during the correlation lecture. The covariance over the variance of the x variable. So the covariance of x and y over the variance of the x variable. Then once you have, for a simple regression, once you have the regression coefficient for your predictor variable, then to solve for the y-intercept, or a, is a pretty straightforward matter. The y-intercept equals the mean for your outcome minus b, your unstandardized regression coefficient, times the mean for the predictor, x bar. So y bar is mean for the outcome variable, x bar is mean for the predictor variable, and b here is the unstandardized regression coefficient, which would have been calculated above. So kind of to visually see what's going on in a regression coefficient, it's easy to see this in a simple regression equation because there's just one predictor. So here we have optimism at 2 months. So this is some data for, I think, treatment outcome data, where we have distress at 12 months being predicted by optimism at 2 months after diagnosis for some condition. And we see that there's an inverse relationship. This line is basically the visual representation of the regression slope, or the unstandardized regression coefficient. So we could see that there's a negative inverse relationship between optimism at 2 months and distress at 12 months, which kind of makes a lot of sense. But you'll notice, even though this line describes to some extent, or summarizes to some extent, the bivariate relationship between these two variables, you'll notice that there are some dots that are closer to the line, right? So those will have less error. So those are the actual scores. The line represents the predicted scores. The slope represents the predicted scores. The dots represent the actual scores. So this score way up here has a lot of error. It's contributing a lot of error to the equation, whereas scores closer to the line, to the slope, are representing only a little bit of error. Ideally, you have less error in your equation. So error can be defined quite simply as the difference between the predicted score on the basis of the equation and the actual score. So every person in your analysis, every case in your analysis will contribute an actual score for the criterion. And we're attempting to model, to predict that score on the basis of the regression coefficient and the constant, which will yield a predicted score. So the closer that predicted score is to the person's actual score, then there will be less error. If it is further away, then there'll be more error. So we think about error as basically the amount of error in predicting y from x in terms of deviation from the regression slope or regression line. So the best fitting line is the one that minimizes the squared errors of prediction from the residuals. So we're attempting to minimize the squared difference from the line. So that's why this is called ordinary least squares estimation, or least squares estimation, most commonly called ordinary least squares regression analysis, because the regression coefficients are calculated such that they basically minimize the squared residuals, the squared error. And the error, again, is the difference between the predicted score and the actual score, which visually you can see in terms of the distance in a simple regression slope from the line. So if on average the errors are quite small, we will be better able to predict y from knowledge of x. But if the errors are larger, our prediction of y from x will be less accurate. So an extension, simple regression is nice to look at in terms of like for educational purposes like right now in order to understand what a regression actually is. But for the most part, when people conduct regression analyses, they typically, though not always, will have more than one predictor involved. So multiple regression refers to when there are several predictors, so more than one basically. We can't simply just add up predictors. You might think, well, we could just run a simple regression analysis for however many predictors we have. Unfortunately, we can't do that because, like we said, there will be some overlap in terms of prediction of the outcome, and we usually want to partial out. We want to statistically control for that overlap. So here we have the equation for a multiple regression analysis. The predicted value for the outcome, or y apostrophe as it's symbolized here, equals the regression slope for predictor 1 times the score on variable x for predictor 1 plus the regression slope for variable 2 times the score on x for variable 2, and so on for however many predictors you may have. It would continue, then plus the constant or the intercept. Don't forget the constant or the intercept, and that would give you your predicted value of y. So this is a linear equation which we would use to determine the predicted value of y. Basically, it could be done for each and every participant, or even scores outside of what was found in your data. However, obviously you wouldn't necessarily need to do this manually by hand. The computer, the statistical program would do that for you. All right, so most of the interpretations of the statistics from a simple regression kind of carry over to a multiple regression. However, there are some unique things that we should mention. So the regression slope is still the change in the outcome. So the change in the criterion or outcome, or y or dv, whatever you want to call it, the change in that for a 1 unit change in the predictor. The main difference here is that now it's also taking into account the other predictors. So it's the change in the outcome for the focal predictor when all other predictors are held constant, right? So we have 3 predictors. Each predictor will have its own coefficient, and it will be interpreted as basically the unstandardized regression slope for that predictor when the other ones are statistically controlled for or held constant. So it's important to note that the slopes or coefficients partial out or statistically control for the other predictors that are in the equation. Now this will still allow us to arrive at a set of coefficients, unstandardized coefficients, that minimize the squared deviations between the predicted score and the actual scores. So it is still a least squares solution. It's still ordinary least squares regression. Another thing that it will do is it will optimize the Pearson's R, basically the correlation between the predicted scores and the actual scores. So it will optimize that outcome, basically make it as strong as it possibly can be. For statistical hypothesis test, there is a fairly straightforward t-test for determining whether or not a regression coefficient is statistically significant. And the formula is fairly straightforward, although it's a bit more involved if you're doing this by hand, because actually if you're doing multiple regression by hand, you would be employing matrix algebra, so we're just not going to go there for now. But in the end, you would take the unstandardized regression coefficient and divide it by the standard error of the unstandardized regression coefficient, which is basically a measure of how much you expect the regression coefficient in your sample to have deviated from its population parameter, its regression coefficient in the population. So that's a fairly straightforward t-test that's given in output for regression analysis, which I will upload an example of how to conduct a multiple regression analysis in SPSS onto Blackboard in a separate link. You can view that, but basically that's how it's computed. It has degrees of freedom equal to n minus k minus 1, where n is the number of cases in the analysis, the number of participants if it's humans. K is the number of predictors in the multiple regression analysis, and then this minus 1 is just to also subtract a degree of freedom for the constant as well. So that's fairly straightforward to conduct the t-test for each and every coefficient. So each coefficient in the equation will have a t-test associated with it. Alright, now the standardized regression coefficient. I've been talking so far about regression coefficients in the unstandardized sense. A standardized regression coefficient is basically a regression analysis, but you put everything in z-scores first, right? So that way a 1 unit change in something basically means a 1 standard deviation change in terms of the original raw units. So the regression coefficient is the change in standard deviation units, or z-score, of the outcome associated with a 1 standard deviation unit change in the predictor. So it's basically similarly interpreted as the unstandardized regression coefficient. The major difference is now we've standardized everything, put everything into z-scores, so that each and every unit basically represents a standard deviation. So it's telling us how much would the outcome change in standard deviation units if a predictor changes 1 standard deviation unit. So that can sometimes make regression coefficients, if it makes sense to do so, it can make them a bit more interpretable and a bit more comparable in situations where it makes sense to do that. So basically, for a standardized regression coefficient, all the predictors are standardized, z-scored, and the regression analysis is run on the standardized scores. Now, you wouldn't actually have to do this. The computer would take care of that for you, but that's basically sort of what's going on behind the scenes, and you interpret everything in terms of standard deviation units. The significance test for the standardized regression coefficient is identical to the significance test for the unstandardized regression coefficient. In the sense that you would get the same answer. So I don't provide the formula for it because it would be the same value for t as you would get for the unstandardized regression coefficient. All right. Another important statistic that results from a regression analysis is the multiple correlation coefficient, which is symbolized by the capital letter R. It's basically the correlation between the observed or actual scores and the scores predicted on the basis of the equation. So what that means is higher, so this ranges from 0 to 1, where a higher value, closer to 1, would mean a better equation. You're predicting more of the outcome, right? A lower value, closer to 0, would mean a poor equation. You're predicting less of the outcome. Just like with Pearson's R, if you square big R, the multiple correlation coefficient, it will give you the proportion of shared variance, or in other words, the proportion of the variance in the DV, or criterion, the dependent variable, or the criterion, that is predicted by the regression equation. So if you have an R squared value of 0.35, that means you predicted about 35% of the criterion. If you have an R squared value of 0.5, it means you predicted about 50% of the criterion, and so on. So that tells you, basically, it's a pretty easily interpretable value for understanding what proportion of the outcome or how good your equation is. It is associated with an F-test, which is very similar to an ANOVA analysis. It actually is an ANOVA analysis. We're not going to get into all the details of the components of the ANOVA analysis of variance for the F-test of the R squared, but just know that it has its own significance test. So it is possible for the R squared to be significant and the individual coefficients are not. More rarely, some of the individual coefficients may be significantly different from 0, but the R squared would not be. Usually, if the R squared is not statistically significant, it's not advisable to interpret the individual coefficients. Usually, if your R squared is not statistically different from 0, so this is basically testing, is our R squared value different from 0? If it's not, it's usually a bad idea to go ahead and interpret the individual predictors, because you basically are predicting nothing of the outcome. So it's based on an F-test where in the numerator we basically have a measure of prediction, or how well our equation is predicting the outcome, and in the denominator we basically have a measure of error, or how much our prediction equation is missing in the outcome. And we're just dividing, as in almost every test we've done in this class, we're dividing the error variance into the effect variance, and we could look up in the F table, or the F value will be associated with a p-value to determine, can we reject the null hypothesis that the multiple correlation coefficient, big R, and consequently R squared, is 0, right? So we want to be able, hopefully, to say on the basis of our equation that we can rule out 0. If we can't rule out 0, then we don't have a good equation, right? So we want to be able to at least be able to say we're predicting significantly more variance in the outcome than 0. Let's take a look at some output from SPSS. There's a more detailed tutorial about regression analysis in SPSS on Blackboard. But basically, there's a ton of output you could request, but we're going to go over the kind of stuff that you should be able to interpret. Basically, you'll get a model summary. The model summary will give you big R, which again is the multiple correlation coefficient, and also R squared, which you can interpret as the proportion of the total variance in the criterion that is explained by your predictors. So we can see in this hypothetical example, we're explaining a great deal, over 90%, roughly, was that 93, or can't tell if that's a 3 or an 8, but roughly, let's say 94% of the outcome is being explained by our predictors. You can ignore for now the adjusted R squared and the standard error of the estimate. They're important, but we won't cover them in this lecture. All right, so R squared, basically the proportion of the total variance in the outcome that is explained by your predictors collectively. Less overlap, of course. And big R is just basically your correlation between your predicted and your observed values for the criterion. So both of these are an index of how good of an equation we have. So the higher those are, closer to 1, the better. So these are really close. The R value is really close to 1. So this is like an amazingly good equation. You won't see anything this good with real data from humans. It's really unlikely to see an equation this strong. Right. We have in our ANOVA table, which you'll recall, the ANOVA tests whether or not your R and your R squared are significantly different from 0, right? That's the null hypothesis, is that they are 0. And we can see, okay, in this one the F value is quite high and the P value is rather low. It's not 0, like if we clicked on this in SPSS we could see what it actually is, but it's rather low. Let's say it's getting pretty close to 0. So we would be able to reject a null here, of course, and say that we are predicting a significant proportion of the variance in the outcome here. So the outcome here is GPA, and our three predictors are intelligence, motivation, and hours per week. So we can see the unstandardized regression slope for each predictor, and we can see the standardized or beta coefficient for each predictor. So what we're seeing here is that intelligence, for every unit of intelligence, let's just say it's an IQ score, that intelligence goes up, GPA will go up 0.045 units, right? And so we can look at the t-test for that and see that is, p-value is 0.032. If we were using a traditional cutoff of 0.05, we would be, I mean it's close, but we would conclude on the basis of these data that we should reject the null hypothesis and say that there is a positive relationship between intelligence and GPA. For the next variable, motivation, the coefficient, the unstandardized coefficient is 0.164, and the p-value for that is also quite low. It's low enough that we're going to reject the null, and we're going to say that motivation is positively associated with GPA, such that for every unit, whatever the scale is for motivation, we're not aware of that right now, but whatever the scale and motivation is being measured on, for every unit that increases, GPA is expected to go up 0.164. After controlling for intelligence and hours worked per week, right? And then hours worked per week, it looks like in this equation, is doing almost nothing. So it's just a useless predictor. We could probably cut it from the equation and it wouldn't do any harm. It might even make it better by cutting it from the equation, at least in terms of the amount of error involved. So we have essentially no relationship between hours worked per week. It does have a very small inverse relationship, but if we look at the p-value is incredibly high, well above any alpha we might use, so we cannot reject the null hypothesis for hours worked per week. We would conclude on the basis of this analysis that after controlling for, and this is a key part, after controlling for intelligence and motivation, the relationship between hours worked per week and GPA was not statistically significant. It was essentially zero. Alright, so here we can see how these values, how these coefficients might be plugged into the equation. So we have y apostrophe, which is our predicted score, equals 0.045, which is our unstandardized coefficient for intelligence, plus 0.164, which is our unstandardized regression coefficient for motivation, plus, and I'm going to, even though this is kind of a useless coefficient, I'm just going to add it into the equation so you can see where it comes from, plus negative 0.009, which is our unstandardized regression coefficient for number of hours worked. And then finally, we have to add the constant, and the constant here is a negative 2.332, which is kind of nonsensical, but it's important to have in the equation. So here, what that really means is that the expected GPA is negative 2.332 if someone has 0 intelligence, 0 motivation, and 0 hours worked per week. So it kind of makes sense that that would be a somewhat nonsensical value. So we could use this equation to compute for any given score. Let's say if this was a really good equation, which for now, well, let's pretend that it is, even though ours is clearly not a good predictor. If there's a really good equation, we could say, okay, if we had someone's IQ and we had someone's level of motivation and we knew how many hours they worked per week, we could estimate on the basis of the equation what their GPA would be. Now, it doesn't mean that it's going to be a very good estimation, but if it's a good equation, it should be fairly accurate if we have the right predictors involved. Alright, so we could plug into the equation an IQ of 105, a motivation score of 3, and 20 hours worked per week. So an IQ, so we have the equation, coefficients. We're saying, okay, what's the estimated GPA for an IQ of 105? You said motivation 3 and 20 hours worked per week. So motivation score is 3, whatever scale that's on, and 20 hours worked per week. All right, now let's not forget the constant, which is negative 2.332. Right. All right. So we'll take 0.045 times 105. That's 4.725 here. And then we're adding to that 0.164 times 3. And that's 0.492. And then we're subtracting a very small value, 0.009 times 20 is 0.18. And then also don't forget subtracting 2.3332. Alright, too many threes there. 2.332. There we go. Alright, so we take 4.725 plus 0.492 plus 0.18. I'm sorry, subtract 0.18. And then finally subtract 2.332. And we get for our y predicted value for that particular case, we get 2.705. So if this was a good equation, which it looked like it was, although it was hypothetical data, we could have some degree of certainty that this person would have a GPA of around 2.705. However, we could also, we're not going to get into it now, but we could compute confidence intervals around this point estimate to see, how precise our estimate might be. So for actually everything we've talked about in this lecture, we could compute confidence intervals for the regression coefficients, the R-squared value. All of them have equations for computing confidence intervals, but we'll just keep it to the basics for now. All right, so last thing I wanted to show you in our kind of brief overview of regression is kind of a conceptual, visual approach to understanding regression. So let's just pretend the variable here labeled as y is our outcome. So whatever you want it to be, GPA, that's our GPA, let's say, and that's the variance in GPA. So just imagine we can pretend that it's represented by a circle. And x1 we could say is our intelligence variable, so we could say, okay, that is IQ. And let's say x2 is our motivation variable. All right. So R squared we could think of as being basically A, B, and C, right? A, B, and C is R squared. That's the proportion of the area, or not the area, the proportion of the variance in Y that's being explained by these two predictors collectively. Now notice C only gets to count once, it doesn't get to count twice, even though it's part of all three variables. Alright, so A, B, and C would be like R squared in this depiction, would be A, B, and C. Right? Now E would be like our error or residual. That's how much of the total variance in Y we did not explain, right? E is how much of the total variance in Y we did not explain. A would be similar. We could think of it, it's not quite this, but we could think of A as basically being our regression coefficient for IQ. Now, why not A and C? Well, because C is overlapping with motivation, so we're controlling for that. That's why that is omitted. And then B, right here, B, we could think of as being our regression coefficient for motivation. So C doesn't get to count in either regression coefficient, but it does get to count in the R squared, but only once, right? It's kind of like a visual depiction of a multiple regression analysis with two predictors. For the most part in a regression analysis, the coefficients, the predictors, are interpreted in terms of their relationship with the criterion after partialing out the effects of the other predictors, right? So that's one of the main purposes of regression analysis, is to see what's the relationship between x1 and y, your predictor and your criterion, after statistically controlling for the other predictors. Alright, now that's been kind of a brief, well, probably not as brief as you would like, but that's my version of a brief overview of of um, of multiple regression and regression analyses. As I mentioned at the beginning, regression is a topic that could really be an entire course, so hopefully this brief introduction at least gives you some idea of what a regression analysis is and how to interpret the results of one. Alright, thank you for joining me, and I hope you enjoyed that as much as I did.